So this is about chassis fabrication. So basically, what is your robot built out of? The lower part, or where the wheels are. There's sheet metal, aluminum tubing, X-slot extrusion, and preferred is C channels. Sheet metal, it can be a classic, it's a standard, quick, reliable, easy build and wheel spacing, robust. There's a lot of help available. It's limited though, and adjustable possibilities without the custom machining, and can be hard to be worked in the pit. But this is the classic standard sheet metal kit. There's custom sheet metal. You can literally customize everything, so that's literally a benefit. Determine the weight, the strength, the tension, everything. But it requires extensive knowledge and support in manufacturing. You need water jetting, laser cutting. There's a lot of work involved with this, and the new designs, they can just be unreliable. Like, you might want to test something and it just ends up failing. Where the other ones, this one is standard and it's you can trust it, basically. Then you have aluminum tubing. So it's adjustable paint gel. It's easy pit repairs, pre-drill holes. It can have problems if it's not designed built correctly. Bearing blocks and gearboxes can come loose over time. So if you're like in a match and some parts come loose, that's not necessarily a good thing. You have X-slot extrusion. It's robust material designed for bolt-to-carry construction. Work well with linear translation motion, which means it can go like this, can go left and right, or this can go up and down. And works well with it. It's heavy. Fasteners can come loose or break free. It's expensive and can be difficult to machine. So this is a perforated C channel. As you see, it's like a C, so that's why they combine things together. This is obsolete. It's wriggly and ugly by today's standards, so mostly you won't see this, but it's quick and it's a dirty build for prototyping. So here are the most common fabrication techniques. Nuts and bolts, you can just do rivet and gussets. For T-locks, this is typically for the T-channel extrusions, and you can weld together. If you'd like to read this, pause the video. Again, if you'd like to read these skills, basically just know about these and understand which one you want, etc. You'll mostly get through this when you are in build season and you'll learn a lot of these skills. Section 4 is materials. So there's a lot of metals. You have aluminum. So there's different types of aluminum. There's like different types of alloy, like 50, 52, 60, 61, 60, 63, and 70, 75 by the numbers here. So let's just get through this. 60, 61 is the most common series. It's going to be mainly with your chassis. It can be, if it's reduced, the strength depends on the bending and the welding. This is capable of being welded or bent without losing much strength. It has reduced corrosion resistance. That's the 50, 50, 52. And then you have the 7075. This is the strongest alloys available. It's ideal for making shafts, stocks, and gears where you want them to be very durable and strong. This is a chart about which metal you want, which type of aluminum alloys. These are all aluminums. These are also some examples in the real life applications. So like the 7075, it's high strength. There's not a lot of workability with it, but that's fine because I'm not gonna weld my shaft into a wheel or something like that. So this is just like your cheat sheet guide for which aluminum alloy you want. And then you have steel. Steel is super strong, but it's also super heavy, so that's why you're going to use them using shafts, nuts and bolts, or high load bearing gears. Like if there's a lot of tension on this, you want to use steel. But remember, you want to keep your robot light, and that's why we use aluminum instead. This is just to my point. So steel is faster and crucial component that you don't want destroyed. aluminum chassis and structural fabrications. Lighter, it's not strong, but that really doesn't matter if you have like 150-pound limit. And it's aluminum's everything else. Steel's only for nuts and bolts and important parts. Basically, plastics. So ABS, machine prototyping. It's easy to paint and glue. If you want to read this, you can. I'll stop a couple of seconds for every time. This is acetyl, so you're gonna mostly see it for bearing spacers, and because it has a good low coefficient of friction and it has good wear properties, so high durability. Again, if you want to pause the video, you can. Polycarbonate, a tough, strong material. It's see-through, it's transparent, and it's ideal for installing control systems because it's high impact, it's transparent, and it can be used as a lightweight substitute for sheet metal. This is UHMW, ultra high molecular weight polyethylene. It has the highest impact strengths. It's typically made to make dynamine, which is usually a cord for elevators and such. PLA, polylactic acid. Basically, that's our uses for 3D printing. These are some skills you want to know, like what's the use of plastics. Especially a big one is that you want to know what metal is used for chassis and structural fabrications and why. It's aluminum. You want to know like once you use which alloy or which metal at least, because that's really important because you don't want to like break that 150-pound weight limit if you're going to use a steel robot. Mechanisms. So there are arms, elevator, lift, and hybrids. For arms, they consist of a pivot point, a bar, and there's an actuator, basically something that moves it, and it's driven linkage. For arms, you gotta learn about torque, which is force times distance. So the greater distance, the more force is needed to match it up. You get the greater the distance, the more torque is needed. Smaller distance, less torque is needed. Real life example: more distance, more torque. Less distance, less torque. And also, if you have more power, you're gonna have more speed. Less power is equal to less speed. Same torque or twice the power result and twice speed when under load. You typically want to design a safety factor of 2 times or 4 times. Again, these are real world examples: more power, more speed, less power, less speed. So these are work envelopes. Operating envelopes are just how fast or how far operating envelopes are how far your arms can move, and restricted areas where your arm should not move. So if you don't want your arm to be moving at 360 because that can be dangerous or can hit something, so you want like a restricted area to make sure your arm isn't doing something crazy. For your arm design, you want to use as lightweight materials as possible because especially at the end, you don't want like 60 pounds on here. You're going to have more torque to move it, so it's going to take more energy, but also because there's going to be a lot more stress and tension, and robots can break. You want to keep things simple, more robots easy to operate, less parts to break or build. Off-shelf items, and you want to use some counterbalances like springs or weights. 4-bar linkages. So it's very similar to the arm, but this bar, this always remains the same place. So all these can move, but except for that one. They go up and down. It's basically like an arm. 4-bar linkages, you want to use as lightweight materials as possible, just like a regular arm. You want to design and control for feedback to see how well it's doing. Again, KISS, keep things simple. Use off-the-shelf items. It's basically like the same from the top. There's some crazy ideas like the double reverse 4-bar. This is just like the more you know. So This one's a double reverse forward bar and can lift over to 8 feet, starting at 41 inches and all in 1 second. Elevator and lifts. So there's going to be two parts. This is going to be the carriage, the moving part, and track, the stationary part. This is the track. These are continuous lifts. So this one, this pulls back, this goes down, this rotates this way. The lifts go up. This goes this way. The lift goes down. The good part is reduced load motor, simple drum side, light cabling. It's slower. Final stage moves up and down last. There's potential for jamming, and cable route is more complex. That is a continuous lift. So after this is done, this goes, and then this goes. There's cascading lift. So they're all attached to each other. So if this goes up, all of them go up at the same time. It's going to be faster. The middle stage are less likely to jam. All sections, they're simultaneous lift. Issues with it is that it's greater load on the motor, increased complexity the bigger it is, and cabling must be maintained regularly. Elevator and lift tips, these are just tips. If you want to read it, pause the video. And then this is the rack and pinion. So motor spins this, it goes up. This is called the rack. The sharp edgy points, that's the rack. The gear, that's part of the pinion. It goes up and down. It's heavy, but it's robust and precise because it can stop at one places. These are scissor lifts, so this is like the cross sections. We'll see how this designs, but just know that this is scissor lift. They scissor lift. This is an example of rack and pinion, but there are other ways to do this. Rack pinion goes up. This goes up. This is an example of how scissor lift works. Scissor lift. The minimum retracted height can go under field barriers. You can be precise on how far you want it up or how far you want it low because you have well, at least in this example, you have the motor with the rack and pinion, so you can see how far up and down it goes. It doesn't deal well with side loads. It tends to be heavy. It has to be built very precise, and the stability decreases as height increases. Now you have a lead screw. So like I said, there are different ways for doing scissor lifts. This is a lead screw. This rotates, and then it moves this back and forth just like the rack and pinion. It's precise, it has locking, and it's relatively simple. And the issue with it is that it's often slow. There's the weight issue, its size, and it's fragile. These are ball screws. These are noisy, complicated, back drives easily, so it could go back like go left, it can go right. Because there's not as much friction. It's precise, it back drives easily if you want that. You won't see anything in this, but you won't see ball screws in FRC, but the more you know. Some hybrid designs. So combining arms connect to the final stage of an elevator. Sometimes you want to use a elevator to lift it and then use the arms to attach to something. There's also a telescoping arm and pivoting elevator, so this goes left and right, but this arm goes extends or unextends and place things. This is a real life example. This went back forth and this arm extended. There's also multiple elevators, so in this design you can go up and down and left and right. There's different directions. There's all sorts of combination we can do with elevator and arms. Some skills. Now you have manipulators and end effects. So for manipulators, there are things that grasp, things that move, and things that store. Right here you have a claw. We're going to talk about things that grasp, and luckily we're talking about claws. So roller claws, these at least these roller claws, they stay in the same place, and they combine rotary motion and the grabbing properties of claws. They're effective at holding game pieces and simple to build. These are articulated rolling claws, so there's a spring here that allows the claws to open left and right. These are stable. These can open left or right, so they can like they can grab things basically. Now you have vacuums. You won't see this often, but there's vacuums. They suck game pieces in to hold on to them. There are latches. There are two different types of latches. So simple latches, you latch onto it, they close. There's no way to open it remotely. There are smart latches that can be remotely released. So to press a button, they can be released. That's basically latches for you. And now you have things that move things. So you have rollers. These rollers, they spin, things roll in, basically. You have shooters, so different types of shooters. You have a one-wheel shooter, you have a two-wheel shooter. So things roll in, it shoots it out, basically. A key point about shooters is that you don't want them to be jammed. So the last thing you want to do is your shooter like being stuck or jamming and not being able to shoot things. That's basically the key things. Like I mentioned before, these are in this picture they're a single wheel shooter. It single shoots. The spin is usually constant, and the distance are variable either by the wheel speed or to change the angle of the guide ramp. The wheel needs to be mounted vertically. Two-wheel shooters, this is determined by speed of wheels. Speed can be varied by relative speed between two wheels, and wheels can be mounted vertically or horizontally. A catapult, by using tension paired with a long lever arm launching game pieces, it's slow but it's effective ways to keep consistent to keep score depending on the game. And you change the angles to see how the distance, again, like I said, slow but consistent. Things that store, hoppers, they carry things, basically. Massive bins were commonly used to the golden era of traditional FRC. The more you know. Yeah, hoppers store things. Helical hoppers, so they have this round gumball design where they roll things. They can store a lot of balls in a single file line. Things move up and down because things move up and down, more or less. Now you have vertical hoppers. So back in the hoppers, they're like in a tub in a box. Vertical hoppers, they go from top to bottom. So the frisbee at top goes down as the frisbees are being launched. Linear path, not very used, but sometimes you might see it just because storability isn't much unless you combine linear path with vertical hoppers or something like that. They're in a straight line, they store things. So I mentioned ago about jamming shooters. This robot, it's not, no. So balls, there's many issues. Balls can weigh down roof. Shooter accuracy can be benefited. The contact with the flywheel is poor, so that can lead to jamming. This area is still prone to jamming into the funneling, and if the motor torque is too slow, then it gets jamming. It does no. If the motor wheel is too slow, it doesn't prevent or clear some of the jammings. So you're gonna have jammings in your shooter, and that's a big no-no. That is it for manipulators. We're going to talk about pneumatics. Pneumatics, compressed air goes through a hose into a reservoir tank. Gets compressed air, all this, then you release it, boom, all the air goes here, pushes this your device, and then the air is gone somewhere else, probably like a release valve. The parts of pneumatics are the air compressor, connects the air tank and pressure gauge, compresses the air to be used as pistons, but it's susceptible to overheating from excessive use. There's the air tank. Everyone knows what an air tank is. This is the air tank. Oh, although they can be chained together to hold more air. A cylinder, so it produces linear motion using the compressed air. So if you compress air, it goes left or right. It uses linear motion. It produces linear motion. It goes up, down, left or right, one direction. This is the solenoid valve. So I believe this is how you get air in. It's the valve that says go with the air. It's the release valve. This is the solenoid valve. So solenoid valve, I believe it's the release valve. So back over here, that's the solenoid valve. You have all this air, but you electronically press a button. It releases all the air. It's basically your switch. That's what the solenoid valve is. This is an onboard setup. So this is like on the robot. This is what it would be. But this is an off-board setup. So the air pressure is not so on the robot. Then the air accumulator tank must be filled in the pit using an FRC legal air compressor. This is just an off-board setup. There are pros and cons to pneumatics. Pros, they're much lighter than motors when several are used, can maintain position at stall without failure, can be used in a more compact environment, actuators can be very fast. They're typically rugged and resistant to impact, easy to set up and install. Superior means of producing linear motion. Cons, they're heavy upfront costs in terms of weight. Excessive air requirement may lead to a higher compression drain on battery, compressor duty cycle, vibration system. You can run out of air or you can overheat with prolonged use. That is Section 7 Pneumatics.